This is the lecture video for section 2.5 in the textbook. And the topic is improper integrals. Our goals in this lecture will be to learn about how to integrate when a function has a discontinuity in its domain. And from this, we'll make a definition of an improper integral. We'll also learn how to recognize when an integral is improper. There will be improper integrals with functions that have discontinuities in their domain, but there will also be other types of improper integrals. The main bulk of this lecture will be in parts 3 and 4 when we learn how to determine whether or not an improper integral converges. And this will be the definition of the value of the integral if it converges, and also learn how to compute that value when it does converge. And finally, we'll learn a short comparison test, a theorem that tells you how to determine the convergence of some improper integral based on the knowledge of another improper integral related to it. So to get started, I want to remind you of something important from earlier math classes. We're going to be using ideas about infinity in this lecture, and this is really what gives the meaning to improper integrals in general, something about infinity. The symbol infinity in math classes implies something kind of vague, but for us in calc class with functions and variables and limits, the symbol infinity implies that something grows without bound. It means that the value of the function or the variable that is reaching infinity in some limit will eventually get larger than any finite number that you choose. Keep in mind that infinity is a symbol representing some concept in terms of a limit. It's not a number. We cannot evaluate it numerically by performing arithmetic operations on it. So we can't divide by infinity. Although sometimes in a limit, 1 divided by something going to infinity might have a meaning. We can't multiply infinity by other numbers. For example, the symbol infinity times 0 doesn't have meaning. It's one of these improper forms that shows up sometimes in certain limits. And we can't do function evaluations with infinity. The meaning of tan inverse or arctan of infinity, this doesn't make any sense the way it's written, although the arctan of x as x approaches infinity may have a meaning as taking a limit of that function. So I encourage you to replace infinities with limits. The limit maybe as t goes to infinity at any point that you feel infinity is showing up. And I'll be really careful to do this in this video to show you, for example. So to start working with infinity in limits, these 6 limits are all taken at positive or negative infinity. These are really horizontal asymptote problems. I just want to remind you how to compute limits as a variable approaches infinity. And along the way, we'll be recapping some of the important features of these types of functions as we consider infinite limits of these functions. If you want to try these on your own, you can pause the video and write a few of them down. I'm going to switch over to tablet mode and work these out by hand. So part A, and again, you can pause at any time and try to solve it ahead of time and compare your answer to what I did. Let's think about the limit in part A. It's the limit as x approaches infinity of 1 divided by x squared. So there's not much to do in this case algebraically. We just have to realize that as the denominator of a fraction gets larger, the fraction itself gets smaller. So as the denominator gets infinitely large, the fraction gets infinitely small, and in the limit that becomes 0. The way to think about this using the sort of vague definition that I gave of infinity, it's a number that, or it's not a number, it's representing that some value gets larger than any possible finite number you can choose. The way to interpret this limit in part A is to say that for any small enough value, just larger than 0, let's say small positive value, any decimal that you choose close to 0, you can always find an x value to input into this expression 1 over x squared that's large enough that will make the value 1 over x squared smaller than that chosen decimal number. So that's what a limit means in general. You can always exceed any threshold by choosing large enough values or choosing values close enough to some target. In part B, the limit as x approaches infinity of square root of x, well, it helps to actually draw the square root function, and I'll let you do that on your own, or you can bring this up on a graphing calculator. But the square root function always increases, and it increases without bound. So the limit as x approaches positive infinity of that function is not 0, is infinity, or this limit does not exist. I'm going to write both of them, and I'll probably write both of them in various places where we need these. Writing does not exist is usually a complete solution to a limit problem like this. Writing positive infinity, maybe I'll even add a plus sign to emphasize this, really tells us what's going on in the graph of the function. Not only does this limit not exist, there's no horizontal asymptote in that direction for the function, but also the values of the function f of x equals square root of x continue to increase unbounded as we move to the right along the x-axis. A different situation happens when we take the function e to the t and take t to go to negative infinity. This is another one you can see from the graph, but if you think about e to the t as being powers of e and we're taking negative powers, that'll be the same as looking at the fraction 1 over e to the t as the exponent goes to positive infinity. So these are actually the same limit. Just like what happened in problem A, the answer here is 0. The value of the limit is 0. And the reason is that for any small decimal number, a small positive decimal close to 0 that we choose, we can always find a t large enough so that 1 over e to the t, that fraction is smaller than that target decimal that we chose. And again, this gives meaning to this limit going to 0, or the limit equaling 0. Part D, we can do things with trig functions. The limit as y approaches infinity of sine of y does not exist. And we can't give this value, or a sort of a vague value like plus or minus infinity, because in this case, the sine function oscillates. This is another one that I encourage you to bring up a graph of sine of y, or sine of x if you prefer, and look at that graph as you move to the right. It's always going to bounce back and forth between all possible real numbers between positive and negative 1. So it's going to hit everything infinitely many times, which means that, well, it can't escape off to infinity. It stays bound, the function stays bounded, and it doesn't approach any single value since it always moves away from that value infinitely many times. Another function that we should recall its behavior is the ln function. As w approaches infinity, ln approaches infinity. So this one has a positive infinite limit, or we can also just say dne, does not exist. The reasoning for this is ln is the inverse function to e, and we saw, well, I guess we didn't write this one, but if we had written e to the w and we take w to go to infinity, then the exponential expression goes to infinity. So on the flip side, if the outputs are going to infinity, the inputs are also going to infinity when we look at the inverse function ln of w. Or you can graph the ln function and see this for yourself. So the last of these is a rational function, and these are good to practice just writing out some rational functions. It's a fraction involving two polynomials. And the way to handle these is to multiply and divide by the largest power of x in the denominator. So here I'm going to underline it twice. There's an x squared. I'm going to multiply, I'm going to divide the top and the bottom of the rational function by x squared, that largest power. We'll take x still to go to negative infinity, and I want to keep my limit around because I have to evaluate it. If I divide every term by that largest power, I'll get 3 plus 7 over x squared in the numerator, and 1 minus 5 over x in the denominator. Now, as we take x to go to negative infinity, each of these resulting expressions with an x goes to 0. So again, the denominator is getting heavier, so the fraction gets lighter or goes to 0. The same thing happens down here, even though we're taking negative large numbers in this fraction. Both go to 0. So finally, the limit evaluates to 3 over 1, which is 3. This is a quick refresher on how to evaluate limits involving infinities. And I encourage you to go look up more practice problems if you want to refresh yourself even more on this. So this is the next problem. I'm going to go back to the slide so we can put this next problem into context. Here's the function, and we'll deal with this on our own in a moment. And the question I want to consider to introduce improper integrals to you is, how do we integrate a function that has a discontinuity? So here's a basic example of a function f of x that has a discontinuity. I've given you the graph of this function. If you ignore the yellow shaded region, the blue graph has a jump discontinuity at x equals 2. And you should be suspicious of this even before you look at the graph, because it's written as a piecewise function. In order for this to be continuous, the left and right limits at 2 would have to be equal, but now you can see that they're not. It's a function though, and we could ask, how do we integrate? How do we take the area under this function? Just by looking at the graph, I hope that a couple ideas occur to you, and maybe write those ideas down or pause the video and flesh them out a little bit in your mind. I'm going to teach you how to integrate this, how to compute this definite integral from 0 to 5 of this function, but somehow we have to deal with this jump discontinuity at x equals 2 in a way that makes sense of the area shown. So if you go on Canvas and find the interactive version of these slides, they're linked there. You can actually play around with widgets like this in all of the slides, and you can slide around the number of subdivisions, the number of rectangles used to approximate this area. We use our same principle of approximating using rectangles, or you could do trapezoids if you like, and then choose left or right or midpoints for the approximation scheme. Then you'll see that as you take more and more subdivisions, something will become clear. I'm not going to be able to show you in this video, but what will happen is if we choose small enough rectangles, we'll start to segment this integral into a piece to the left of the discontinuity, the bit under this curve. If we remember, this is the curve y equals 3x squared. And then the rest of the rectangles will fall under this triangle shape, this straight line with negative slope, which the formula is on the other slide. So as we take more and more rectangles, they'll sort of self-separate into the two pieces of the function. And hang on to that thought, because we'll use that in order to evaluate the function in a moment. So one thing we might worry about if we're using rectangles to approximate things is that when we take the limit of the Riemann summation formula, again, we're summing up rectangular areas and taking the limit as the base width of each rectangle goes to 0. We might worry that this limit actually doesn't exist. It turns out, and this is a really expansive interpretation of Riemann summation that has the most utility in calculus beyond just continuous functions, that as long as a function has finitely many discontinuities, only finitely many places where we have a jump like that or something else going on, then the integral will exist. The limit of this expression will exist, and then that gives meaning to the definite integral from a to b. In our case, we'll try to integrate from 0 to 5 and deal with that discontinuity at 2. Another thing to consider is somehow we'll be able to use the second part of the fundamental theorem of calculus to evaluate once we decide how to split up our region. But another thing to consider, this comes from the first part of the fundamental theorem, is how we can make sense of an antiderivative of a given function. Remember that an antiderivative is a function capital F of x, whose derivative equals our given function, in this case, little f of x. Well, if we set capital F to be the definite integral from 0 to the input value x of f of t dt, this is actually, by the first part of the fundamental theorem, the surefire way to get an antiderivative of any function. Capital F here is an antiderivative of little f, except capital F of x may not have a derivative everywhere, because at certain points of discontinuity, the integral may not be defined, or the integral may be defined, but little f may not be defined or may have a jump or something else. So the only issue here really is that capital F may have issues at discontinuities of little f. However, we can still make sense of capital F on smaller intervals that miss the discontinuities, in which case capital F on those smaller intervals will still be an antiderivative function for our original function. So all of those theoretical concerns aside, we don't necessarily have a single capital F, an antiderivative of our little f that we started with. I'll show you the definition again in a moment, that piecewise function. But we want to come up with a way to evaluate this definite integral, making sense of taking limits as the base width of rectangles go to infinity, or making sense of this region in another way. So let me show you this whole function again. So this is the question we want to answer. How can we make sense of this integral from 0 to 5 of the function? Here's the graph of the function and the algebraic definition of the function again. And one way to think about this is if we approximate with small enough rectangles, and we can approximate on both sides, if we shrink things down so that we can approach the discontinuity with rectangles from the left or the right side, and then we take those rectangle widths to go to 0, we'll actually get a precise approximation of this area. The way to express this carefully using limits is to take, I'm first going to take an integral from 0 up to the discontinuity. I'm going to call the upper limit b and take a limit as b approaches 2. I'm even going to emphasize I want to approach 2 from the left side or from below. So we'll take b approaching 2 from the left of f of x dx. And that's going to capture the left side of this region. On the right side, I'm also going to take a limit, and I'm going to start at 2 here. So I'll let the lower limit be a, and we'll go up to 5 of f of x dx. And here I'm going to approach 2 from the right. This integral will capture the right side of this figure. We're not going to do every problem like this. This is just to set things up and make sense of an improper integral. This is an example of an improper integral since we don't have a single antiderivative function capital F to do the fundamental theorem of calculus with. But also if it has a discontinuity, we'll just call these things improper. So how do we evaluate this? Well, notice that on the interval from 0 up to 2 or anything to the left of 2, so for any interval 0 to b where b is less than or equal to 2, I'm integrating from 0 to b, but the function here, when x is less than or equal to 2, has values given by 3x squared. On the other hand, as a approaches 2 from the right, we're looking at intervals of the form a to 5, where a is greater than or equal to 2. In this case, we can take a to be greater than 2, and this integral will still make sense. In which case, we're dealing with the second part of the piecewise function, 10 minus 2x dx. So now we have 2 different integrals to evaluate. I'm going to keep my limits around, and we'll have to plug those values in eventually, or somehow evaluate the limit. So as b approaches 2 from the left, we can integrate this function. This is an easy power rule. We'll get x cubed evaluated from 0 to b. On the other hand, let's keep our limit as a approaches 2 from the right around and evaluate this in this definite integral, which should be from a to 5. I forgot those. This will be, let's see, 10x minus x squared, again, evaluated from a up to 5. So here we go. We have 2 computations, 2 fundamental theorem evaluations to work out, and then we'll substitute in to solve the limits. So we have the limit as b approaches 2 from the left of b cubed minus 0, just leave that as b cubed, and a approaching from the right of, let's see, 50 minus 25 minus 10a minus a squared. And now what's left to do is solve these limits. Because everything in sight is a polynomial function, we can directly substitute in b equals 2, a equals 2. So here we'll get 8. And in this expression, we will get, let's see, 25 minus, as a approaches 2, we'll have 20 minus 4. And let's see, okay, 16 minus 8. I think that looks like 17 to me, but you should double check. I'm going a little fast here. So apparently the true value of this definite integral expression, which is an improper integral, just to emphasize, this is improper, since the function has a jump discontinuity at x equals 2, but we can still make sense of the value of this definite integral, and the value is 17 according to our computations. Let's put this on even more rigorous ground before we explore more examples. By that, I mean we should make a formal statement about how to evaluate any definite integral around discontinuities. And here's the way that we're going to do it. If f is discontinuous at some value x equals c in our interval we're considering, if we're looking at the integral from a to b of f of x and c is in the middle, then we can split up the integral at c and take two integrals and compute their limits from the left and the right side. First, we can integrate from a to t and let t approach c from the left. That's this first integral expression here, just like we did in the previous example. And second, we can compute the integral from s to b and let s go down to c from the right. As long as both of these limits exist, which in the previous example they did, we computed values of them, then we will call this the true value of the definite integral of f of x over that region. You should take this as a definition. And in the previous example, I kind of started with this as our starting place, and I did that for a reason. We had to make sense of the area under the graph somehow, and this made the most sense for us. From now on, this will be the true definition. One thing to clean up our computation that we can use, it seemed sort of artificial that we even needed to use limits to begin with, even though we wanted to approximate the value and then take the limit as those base width rectangles went to 0. But one thing to notice is that if two functions f and g are defined on an interval a to b, and they have the same values, except for maybe a finite number of points, then integration theory tells us that the values of their definite integrals on those intervals are the same. For example, here's just a quick sketch of what could happen. If f looks like this, just a straight line, and g looks like nearly the same, nearly the same expression, except it has a jump discontinuity, or rather a removable discontinuity, not a jump, at a single point. So if f is blue and g is red, these will have the same definite integral value along this interval. And the reason is that when we're integrating, we're computing an area under a function, and area doesn't care about single values at points, it only cares about two-dimensional measurements. So you can think of this as removing the area of a point or changing the area at a single point, which, since points don't have areas, they're zero-dimensional, this won't affect our answer. There's some more rigorous proofs of this that you can find in the textbook. So let's see. Sorry, my little blue graph isn't going away, but hopefully it's not too distracting. So what this means for us is that as we take limits in these discontinuous integrals, these improper integrals, we can actually just directly replace those limits with the actual value at that bound. And the reason is that the integral from 0 to 2 doesn't care if we include or disclude the value at x equals 2 of this function. For example, if we go back to the graph, the function is defined everywhere defined at all x values from 0 to 5. However, the left branch of the function is the one that gives us a value at x equals 2. The right branch of the function has an open circle. We haven't defined things at x equals 2 there. What this means for us here is that the true value of the integral on the left or the right portion of the function we're integrating doesn't care if we use x equals 2 in that domain or not. You can think of this as the difference between integrating over the interval from 0 to 2 as a closed interval, or from 0 to 2 as an open interval. And the previous theorem says that the values of the integrals are the same either way. So we can use this, and we can use a similar thing from 2 to 5 in place of the closed bracket intervals to integrate over, and it'll give the same answer. Most discontinuities can be handled this way. So we can directly jump to these two integrals, and we ended up solving these. We don't even need to plug in, b approaching 2 or a approaching 2 from above. We can just solve these as ordinary definite integrals using the power rule. There's one type of discontinuity that we have to handle separately, which is the notion of a vertical asymptote. If our function has a vertical asymptote, then we will definitely want to call its integral from a to b an improper integral. There's something to deal with, something to evaluate here. And I'm going to be pretty loose with the term improper integral. Basically anything that's not an ordinary fundamental theorem of calculus, capital F of b minus capital F of a computation, we'll call improper, including those things with discontinuities. Although when we separate into the left and right branch of this function, they become ordinary proper integrals that we don't have to worry about with the discontinuity anymore. With a discontinuity such as a vertical asymptote, that's not removable or jump. It's a limit as x approaches c of positive or negative infinity. The function, or rather the definite integral, is definitely improper, and we have to figure out a way to evaluate this. So let's do this one together. If we treat this using the same methods that we did before, how should we think about the interval from 0 to 4 when we have a vertical asymptote somewhere? Well, the first step is to maybe graph the function and see where the vertical asymptote is. So 1 over root x, 1 over powers of x in general look like the following in the first quadrant. And there's a vertical asymptote of this function at x equals 0. So in fact, the area that we want to find from 0 to, maybe I'll put 4 over here, is really an infinite region. It's going all the way up the axis here and stopping at 4. How do we make sense of this? And if we can find a finite value for this blue area I've shaded, then we'll call that the value of this improper integral. Well, one thing that we used in the previous problem to handle jump discontinuities is taking a limit as our x values in the integral get close to that bad value, that discontinuity. So in this case, what it makes sense to say is, or it makes sense to do, is to take a limit as the lower bound of integration approaches 0 from above. Now let's integrate the function from a up to 4. I'm going to rewrite the integrand, by the way, as x to the minus 1/2 dx. And what's useful to visualize here, we'll have some more visuals in a moment, is the following. If I put a here and we slide a to the left, so come in from the right to approach the asymptote at 0, what we're really doing is computing these finite areas under the graph from a to 4 and taking a limit of each of those those numerical answers, which we know exist, as we let the lower bound approach 0. So this is really giving meaning to an improper integral visually, and algebraically, or in a formula, this is the type of thing we'll want to set up. Let's go ahead and compute this whole expression. First, the definite integral from a to 4, and then the limit as a approaches 0 from above. A approaches 0, we're going to hang on to that for a moment. This is a power rule integral we can solve. X raised to the 1/2. We're going to raise that power by 1, that'll be x to the 1/2, and divide by 1/2, that's the same as multiplying by 2, and integrate from a to 4, or rather evaluate from a to 4. So I'm going to plug those in before we evaluate the limit. If I plug in 4, that'll give me 2 times square root of 4, that'll be 4, and 2 times the square root of a. And what happens to this whole expression now as a approaches 0? Well, as a approaches 0, the square root of a also approaches 0. And it's important that we're approaching from above, or from positive values above 0, because the square root function isn't even defined for values to the left of 0. But in any case, this last expression goes to 0 in the limit, so we're left with an answer of 4. So this blue area, we can now give meaning to. It has an area of 4, even though it stretches infinitely up the y-axis vertically. We can still say that it has a finite area of 4, if we make sense of it as the limit of these finite integrals, these finite areas shaded in red, as a slides to the left. So this is what we mean by an improper integral with a vertical asymptote. We will also learn about improper integrals with horizontal asymptotes, or as our function approaches infinity to the right. We'll do that in a moment. But for now, here's another picture. This is computer generated. And if you want to slide this slider on the interactive version of the slides, you can see how the area really creeps up the y-axis. Nevertheless, we just determined that the value of that yellow region as we slide t to the left, and they use t instead of a here, will approach the value of 4. Computationally, you can set up computer programs to compute these integrals and then have them spit out a value for every t that you choose, maybe from maybe powers of 1 over powers of 2 that get smaller and smaller as you approach 0 from the right. Or you could just use any rational number, maybe of the form 1 over n as n gets large. And you can compute the values of these integrals and use those as approximations to the true value of the limit. You'll see that the true area is 4 and our approximations will approach 4. And it'll be interesting to see if those approximations are over or underestimates. I'll let you think about that as well. So the main idea, the takeaway from this example and what we'll use as our definition or rather our computational method for an improper integral in general is if we have any discontinuity, any issue in the domain of our function that we're trying to integrate, we can introduce a dummy variable. I used a and b for upper and lower bounds of integration. You can use any variable you want. The textbook uses a t. And we can take the limit as that new variable t approaches our bad spot in the domain. If c is a discontinuity, we can let t approach c. If the limit exists, the limit of whatever resulting integral expression we evaluate exists, we'll say that the integral converges, just like limits converge if the value exists. Otherwise, we'll say that the integral diverges, and a divergent improper integral has no meaningful value. There's no finite meaning to the area under a graph if its improper integral diverges. So far, we've been computing finite regions, definite integrals over finite intervals from a to b. We can approximate these with rectangles, but we don't yet know how to integrate over infinite intervals of x values, such as from a to infinity. This will be our next task. It's also a type of improper integral in that part of the definition of the definite integral doesn't make sense. It doesn't make sense to go from a to infinity because we can't plug infinity into functions. So rectangles are not good enough to approximate the area that we want. But if we were to cut off our infinite region, so if we go back here and we cut things off at 8 or cut off at 9 or cut off at 10 million, and we wanted to approximate this integral from 3 to infinity by truncating at a finite value, we could actually make sense of that value. So the integral from a to t, where t is some cutoff value of f of x dx, makes sense. If there are any discontinuities along the way, we can handle those as we did before. But if it's a continuous function the whole way, this is the area under the graph from a to t. And like we did with discontinuities, if we take a limit to resolve this issue, and then hopefully we're able to take the limit of some resulting expression in the end, this will give meaning to that integral symbol. We'll call this an infinite improper integral. You can think of this as sort of a horizontally improper integral, or something like a horizontal asymptote we're trying to compute along. This will be an integral that we write as a definite integral from a to infinity of f of x dx. Notice now that this upper bound is not a number, it's infinity, and we'll evaluate it as follows. The integral from a to infinity of f of x dx will have a value if the limit as t approaches infinity of the integral from a to t of the same function exists. If this limit does not exist, then we'll say that the original improper integral, this symbol here, has no value or diverges. So the same language applies for any limit process like this. If the value exists, then that symbol converges and has that value. Otherwise, we say it diverges. Notice that we can go off to positive infinity, moving to the right along the x-axis. We can also go to negative infinity, and here we'll let the lower bound be evaluated as a limit, in this case, as t goes to negative infinity of that definite integral expression. So to practice this, here's a practice problem. If you want to pause and try this yourself, try to at least set up the limit expression. That'll be our first step together. That makes sense of this improper infinite integral from 2 to infinity of 32 over x cubed. So pause the video now and try to write this down. I hope that everyone will do this before I show you the answer. Okay, now that you've at least set up the integral yourself, if it looks like a limit that you, or rather a definite integral that you know how to solve, and then you want to try to compute the limit after, pause the video again and continue on and finish the problem, and then you can look back and compare to what I did. So now I'm going to set up this integral, right, inequality. It's the same expression here. As a limit, as the upper bound, I'm going to use b instead of t, just to emphasize it's the upper bound in this integral. The integral from 2 to b of 32 over x cubed dx. And again, what we've done here is we've said we don't know the area under the graph of this function from 2 to infinity because that's an infinite area. It has infinite length, for example, or we would need even infinitely many rectangles, even if each of them only had width 1. We would need infinitely many rectangles to stretch out, and we don't know how to add up infinitely many areas. However, if we cut things off at some number b above 2, we could add up finitely many rectangles and get an area for, get a number for that area. We could take the definite integral. And if we slide that b value to the right, then we'll use this as an approximation to the true value. And in the limit, we'll reach the true value of this definite integral. So let's work this out together. I'm going to keep my limit around until I actually evaluate it in the end. So usually the last step will be removing the limit symbol by evaluating it. Meanwhile, we can integrate this. This is 32 times x to the minus 3. So the power rule says move that up to x to the minus 2 and divide by minus 2. That'll give us a negative 16 times x to the minus 2, or negative 16 divided by x squared. We're evaluating from 2 to b. Let's keep our limit outside and just worry about how to plug in 2 and b. If we plug in b, we'll get negative 16 over b squared. And then we're subtracting negative, so I'll say positive 16 over 2 squared, or 4. And now we're at a position where we can evaluate this expression as b goes to infinity. And luckily we did that warm-up problem where x went to infinity of 1 over x squared. That's actually the same form as this limit. This fraction goes to 0. I like to think of, I think I said this before in this video, I like to think of this as a fraction whose denominator is getting heavier, so the whole fraction gets lighter as b goes to infinity. In any case, the fraction goes to 0, and what we're left is 16 over 4, which is 4. So I'm going to give you a really rough sketch of this graph to visualize. Here's 32 over x cubed. Looks awfully similar to my 1 over root x, and that's because I'm not drawing to scale or anything. But if we started at 2 and went to infinity, and we kept going, it would get squeezed along the axis there. This has a value of 4, apparently, according to our computations. This is the only way the only method we have to assign a value to infinite areas like this. So there we go. If you did this one on your own before looking at the answer I got, how did you do? If you got the same answer, then great job. And if you didn't, can you see where you went wrong and what you can improve for your next problem you'll work on? By the way, here's a much better picture of this, actually drawn by a computer, of 1 over x cubed. And then you can scale this up to get 32 over x cubed just by multiplying all of the y values. And you can play with this widget on the interactive slides. You can slide t closer to 2 and see these very small finite areas that are maybe easier to compute with less rectangles, but further from the true answer. And as you slide t to the right, it'll keep picking up a little bit of area, but the additional area gets smaller and smaller. So the true value is approximated by taking large t values. One more thing we can do, and we won't do an example together where we slide t off to negative infinity, but we could try to integrate some function over the entire real axis. Draw a function and compute the area between it and the x-axis over the entire real number line. That's something we haven't done before. And the way we'll do this, and I really want to emphasize that this is the only correct way to do this, is to integrate the function up to some value a, some cutoff value a, somewhere between negative infinity and infinity. So it needs to be a finite number. And then from a, we'll keep traveling to the right and go all the way up to positive infinity. Or in short, we want to split an entire real number line improper integral up into a left piece and a right piece where a is the same cutoff for both integrals. Each of these is still an improper integral with infinite limits, but now each of them can be solved by a separate limit. The limit as t goes to negative infinity and the limit as s goes to positive infinity. We'll do one of these problems together in a moment. Using the same terminology as we did for previous limit type expressions, we'll say that the entire expression, the entire integral from negative infinity to positive infinity converges if both of the two split off integrals converge. And if either one of them diverges or they both diverge, we'll say that the full limit or the full integral does not exist or diverges as well. So again, it needs to be both to converge and either one to diverge. Here's an example. Let's compute the value of this improper integral from negative infinity to infinity of f of x dx, where f of x is this piecewise function. Before I switch over and show you how to compute this, can you set up the first piece of the puzzle, which is splitting this up into two separate integrals? You should be always a little cautious when you see a piecewise function and think carefully about what's going on at the seam or the place where it splits into two pieces. But in this case, hopefully that gives you a hint at where to split, what value for a to choose to split up our integral into two improper integrals. Okay, so let's do it together. Notice that at x equals 1, we have a seam or a split in the function. So in order to split our improper integral into two pieces, let's integrate from negative infinity up to that seam 1, so we'll let a equals 1 of f of x dx, plus the integral from 1 up to positive infinity of f of x dx. Now notice that the function to the left of 1 has these values, so we're just going to use that function e to the x in this piece, and then for the other piece we'll use the other definition of f. So the first step, by the way, is to replace each of these improper integral expressions with a limit. And here I have a lower bound for the left integral. I'll use a for my lower bound. So we're integrating from a to 1, and a is some number less than 1. And for these values, e to the x is the name of this function. And then for the second integral, I'll integrate from 1 up to b, where b approaches positive infinity. You can use any letters you like. You can use s and t like the textbook and the slides do as well. For this portion of the function, if b is larger than 1, our x values are larger than 1, so we'll integrate the function e over root x, which is the same as e to the x, e times x to the minus 1/2, just to make our integral computation a little faster in a moment. So keep our limit. By the way, I've set up two limit expressions, and to practice the techniques we've been using so far in this video, pause the video and try to solve one or both of these yourself. Get all the way down to a numerical answer if possible, or show that the limit does not exist. So I'm going to evaluate both of these and then try to evaluate the integrals first and then try to evaluate the limits if I can. E dx has antiderivative e to the x, and we'll evaluate from a to 1. Meanwhile, e times x to the minus 1/2. We just integrated x to the minus 1/2 before. That'll give us 2x to the positive 1/2, or 2 times root x, and then e is just a constant here. We'll evaluate this from 1 to b. So let's plug in our integral values. We have e to the 1 is e minus e to the a. We'll deal with that limit in a moment. Notice that I'm keeping my limit symbol around at every step until I'm done with it. This is 2e to the square root of b minus 2e times 1, sorry, 2e times root b, and then 2e times 1 is just 2e. We evaluate these limits. Again, one of the practice limit problems we did said that as the exponent goes to negative infinity, e to that exponent goes to 0. So go back and look at that first 6-part problem we worked on together if you don't remember. So this whole expression goes to e, or in other words, this limit exists. So one of the two improper integrals converges. But remember, for the original double infinite integral to exist or to converge, we need both pieces of its integral, or both of the separate improper integrals to converge. So we need to deal with the second one. And unfortunately, as b approaches positive infinity, this was also one of the warm-up exercises we do, this piece goes to positive infinity. So this integral does not exist or diverges. So the whole expression diverges, even though half of it converged. If we wanted to give meaning to this area, this is, I'm going to put this in quotes. The actual integral here is equal to positive infinity because the area that we add up from negative infinity to 1 is a finite area and it's positive, but everything to the right diverges to positive infinity. The value of the values of the areas as we slide b off to the right more and more will get larger and larger. So the total area that we add up will be positive infinity in the limit. Okay, there's one more thing that I want to discuss, which is, and here, by the way, here's a graph with the two shaded regions shown. And in the widget, you can slide S and T off to the left and to the right, respectively, to see how these areas change. So this figure here, if we integrate under the graph from negative infinity to positive infinity, we just showed does not have a finite area, or the area where the improper integral diverges. There's one more question I want to talk about, which is why don't we just take a single limit as both limits of integration slide off to the infinities together, sort of at the same rate? There's an issue with this. So I'm going to use the integral over the entire real number line of the function x cubed as a test case to show you what goes wrong. But I just want to remind you that the only way to do these problems, the integral from negative infinity to infinity of any function, is to split up into two integrals, each one with a single infinity in its limits, either negative or positive infinity, and to handle those separately. And the only way for the entire integral to converge is if both separate integrals converge on their own. So here we go. Let's see what happens if we do things the correct way. First, let's actually get a value for this integral. And then we'll compare it to what happens if we slide both of our limits off to the infinities at the same rate. That'll be the second part of the problem. So the first step, and again, try to do this one on your own. Pause the video right now and set up two separate integrals, evaluate them, and take their limits as the bounds go to the infinities. I'm going to do everything in one step. I'm going to let the left bound a go to negative infinity and integrate. You know, this is a continuous function everywhere, so I might as well go from a to 0. I'll cut things off right in the middle of the number line. And then my second bound, I'm going to take to be b and let that go to positive infinity and integrate from 0 up to b. And let's see what happens to this function as we integrate. So a is approaching negative infinity. This becomes x to the 4th over 4, evaluated from a to 0. And likewise, same expression, x to the 4th over 4, evaluated now from 0 up to b. These are two separate limits. Okay, limit, moving a little faster here, just to get to the punchline. If I plug in 0, I'll get 0. If I plug in a, I'll get a to the 4th over 4. Okay. Something similar happens here. If I plug in b, I'll get b to the 4th over 4 minus 0. Easy enough. What happens to each of these expressions as a or b approaches one of the infinities? As a approaches negative infinity, a to the 4th is going to be a large positive number. This actually goes to infinity, so this does not exist. Okay, full stop. The entire integral diverges because one of the two pieces diverged. This integral diverges. But also the second integral diverges as well. So just to be really thorough, let's see what happens in both pieces. They both do not exist because the integrals diverge. Okay, so this improper integral does not have a value. It diverges. The area, the signed area, in this case, x cubed has positive and negative values over the whole real number line. The signed area does not exist. However, if we tried to take a single limit as t, the upper and lower bounds went to the infinities, we'll go from negative t to t, and you can think of this as, actually I need some negative values in here. You can think of this as follows. Let's see what our graph sort of looks like. You can think of this as picking a distance away from the origin and just integrating these little chunks. You'll see that the signed area of each of these finite integrals from negative t to t is 0. The reason is actually that x cubed is an odd function. We'll work it out algebraically in a moment. But this is misleading because we just saw that the full integral diverged and each of these finite integrals will be 0. So in the limit, they should stay 0. And that's a contradiction. So this can't possibly be the right approach. Nevertheless, just for sake of learning, let's compute this together and show that we get the wrong answer. The true answer is diverged, and this is going to be giving us something else. So the limit as t approaches infinity, same integral x to the fourth over 4, evaluate from negative t to t. Keep our limit around until the end. If I plug in t, I'll get t to the fourth over 4. If I plug in negative t, well, it's an even power of x, so I get positive t to the fourth over 4 again. And that's the whole issue. This expression is 0, and the limit of 0 is 0. So we got the wrong answer. In another world, in another set of mathematical laws, we might say, this is actually the way to make sense of an improper integral. So the true area under this graph, the signed area, should be 0. It kind of makes sense, like the whole right half of the picture is identical to the left half. And if we treat the positive stuff as a positive area and the negative stuff as a negative area, they should cancel out. The problem is infinities are notoriously tricky. And when we have limits floating around, we should be really precise about what we mean. If instead of taking the same identical piece to the left, we took something that was twice as big, or we took 2t distance to the left and integrated, and then we slid our two limits off to the infinities left and right, then we wouldn't actually cancel things out. And these would overpower the positive wedges that we integrate, in which case we should get a negative answer. So in some sense, if we compute things that way using a single t value and sliding it at different rates to the left and to the right, then we should be able to get any possible value between negative infinity and positive infinity, including 0 like we got in this case. That's not a good thing. We shouldn't be able to take a limit and have it take on multiple different values. We want a single value, and if it's possible to do different things and get different answers, it's usually an indication that the real definition of the improper integral will give you a divergent integral, which is what happens in this case. Let's wrap everything up with a couple recap questions. Thanks for tuning in. By the way, here's a picture again. You can play with the widget here, where if you slide the right value positive t, it'll automatically change the left value negative t, and you'll see that each of the integrals over finite regions are 0, but we showed that if you separate into two different integrals with a and b as different bounds going to the infinities, you'll get a divergent improper integral. So this is the takeaway. Don't use the shortcut. Oh, one more thing we do before we do recap questions is a small interlude on comparison test. So one thing you might remember from calc class, and you can draw pictures to convince yourself that this theorem is true, is that if g of x is greater than or equal to some function f of x, we'll say that g of x dominates or is on top of f of x on an entire interval of x values, then the integrals have the same inequality. Then the area under the graph of g is greater than or equal to the area under the graph of f on that interval. The intervals have to be the same, but the functions, if they have an inequality, will preserve that inequality. And these are signed areas, by the way, but I'm usually visualizing things as area under a graph in my head. Another thing that you might remember all the way back to the start of calc or even pre-calc with limits is if we have two functions f and g, and g is always larger than or equal to f for at least some range of x values near some limit we're trying to compute, then the limits have the same inequality. So the limit of one function, the limit of the smaller function as x approaches a is less than or equal to the limit of the larger function as x approaches a. You can think of this as the squeeze theorem for limits. What can we say about two functions f and g? And maybe we don't know their antiderivatives, but we do know some relation between f and g, such as g is greater than or equal to f on some interval. What can we say about the convergence or divergence of the improper integrals from a to infinity of each of these functions? I'm going to leave this as something that you can write down yourself using the two previous pieces of information. And notice that an improper integral, again, in this lecture video, is the limit as the upper bound goes to infinity, and it'll be the same limit in each of these cases. So if you use, if you use the second theorem here to deal with the limit, and use the first theorem to tell you about a relation between the two definite integrals in each limit, this will give you a full statement of something called the comparison test for improper integrals. There are similar comparison tests if we let the lower bounds go to negative infinity, and if you have both bounds as positive and negative infinity, then you'll have to split up into two different integrals and make two separate comparisons. This is a technique that allows you to extrapolate information about improper integrals without directly computing them, which might not be possible if you don't know an antiderivative of either of the functions. So here are some summary questions to think about. First of all, what is an improper integral? We've given a few examples in this lecture video, but see if you can come up with a concise description of what it means to be an improper integral. Second, under what conditions do we have an equality between the integrals of two functions over the same x values, a to b? Third, what does it mean for an improper integral that you talked about in question 1 to converge or diverge? And finally, related to the last couple slides, if we know that some integral of a function g of x dx from a to infinity converges, what would we need to know about f of x to guarantee that its improper integral from a to infinity also converges? And I'll leave you with one practice problem that has 3 parts related to improper integrals of, in this case, a function that relates to arctan or inverse tan function. Okay, thanks for tuning in, and I'll see you next time.